Humankind is entering a new era of space travel. Astronauts are set to return to the moon before the decade is out. And scientists and visionaries say humans will soon set foot on a foreign planet for the first time, Mars.
We already visited the moon back in the 1960s and 70s. Nowadays, everyone is talking about flying to Mars. Why is this? Well, it's actually quite simple. Mars has a solid surface. This means we can walk around on it. And even more importantly, the temperatures there are reasonably tolerable for human beings. And that's precisely the reason why life could potentially have evolved on Mars many billions of years ago. We just need to fly there and have a look. And we're familiar with the technologies we'd need to do so. This means that Mars is a feasible distance away.
July 30th, 2020. An Atlas V launch vehicle lifts off from the Kennedy Space Center in Florida. An hour later, the spacecraft separates from the upper stage of the rocket and sets course for Mars. On board, the rover Perseverance. It's NASA's most ambitious mission to the red planet yet.
Mars is very interesting because it's a relatively large planet. In the past, the conditions on Mars in terms of atmosphere, temperature, and so on were quite similar to those on Earth. But we don't see any Martians wandering around there today. So was there once life there or not?
NASA has already sent around 40 successful missions to Mars, including 4 rovers. These spectacular images were transmitted to the Earth by Curiosity. But up until now, all of the probes and Mars rovers have only encountered a cold, lifeless desert world. The planet's atmosphere is thin. Its density is just 1% that of Earth. And it consists of 95% CO2. Cosmic radiation, 30,000 times stronger than on Earth, bombards the surface, and it's cold.
You have to imagine Mars as being like a polar desert. It's incredibly cold and incredibly dry. There's no air to breathe. The average temperature is around -60 degrees Celsius, and it drops as low as -133 degrees Celsius. But it can climb to around +20 degrees at the equator in summer. But it's very inhospitable on Mars.
None of the Mars missions thus far have found any evidence of life. This is now the job of Perseverance. The 6-wheeled robotic vehicle is about the size of a compact car and has extremely sensitive instruments on board. These include 19 cameras, ground-penetrating radar, various analytical instruments, X-ray detectors, and 2 microphones. With all that, the rover should be able to detect the traces of ancient life forms, assuming they once existed.
It's actually quite possible, because at the exact same time that life was emerging on Earth, namely 3.7 billion years ago, habitable conditions prevailed on Mars. We've conducted a lot of tests in the lab, and they indicate that microorganisms could have actually been able to form and survive on Mars. The missions we're sending there now should provide the answers.
The spacecraft with the rover will travel 470 million kilometers in more than 200 days to reach Mars. And that's the easy part of the journey. The landing maneuver is the real challenge. NASA engineers describe this critical phase as the 7 minutes of terror. The probe with the rover hits the Martian atmosphere at around 20,000 kilometers per hour and gets rapidly slowed down. For the first time ever, NASA not only released an animation of the landing, but actual video footage. It shows the lander hurtling towards the Martian surface. At 1,500 kilometers per hour, the landing parachute opens. However, because of the thin atmosphere, it can't slow the descent of the probe sufficiently. At an altitude of around 1.6 kilometers, the actual lander unit with the rover is released. The retro rockets ignite. The lander's descent slows further. At around 20 meters from the ground, the sky crane lowers the rover to the Martian surface. Touchdown! Shortly thereafter, Perseverance transmits the first pictures of the Martian surface. And for the first time ever, a rover sends to Earth an audio recording from a foreign planet. This is what the wind on Mars sounds like. Now the mission proper begins, the search for traces of life. Mars is a little more than half the size of the Earth. Where is Perseverance looking for these traces?
We are primarily looking in places where we have proof that there was liquid water, and especially where there was water for a very long time. The best examples are former Martian lakes, which we identify from the depressions they left, like impact craters, of which there are many, and into which a former river valley flowed, and, above all, where a delta has formed at the mouth of the river.
Wherever there's liquid water, we find life. At least on Earth. Water is an excellent solvent. It allows molecules to intermingle and biological compounds to form. And there used to be water on Mars.
We've since discovered that Mars wasn't always so cold and dry. For a long time it was thought that it used to be warm and wet. We now believe, or rather know, that it was cool and wet instead. So temperatures were around freezing point, sometimes below, sometimes a little above. And there was liquid water, and an atmosphere that was dense enough to keep water liquid on the surface of Mars.
Scientists speculate that a fifth of the Martian surface was covered with water for at least 1 billion years. That's an area 3 times the size of the USA. Perseverance cannot search over such a large area. Where are the best chances of finding traces of life? Tips are being provided by the Mars Reconnaissance Orbiter. The satellite is orbiting Mars at an altitude of 300 kilometers. And former lakes and rivers can clearly be made out on the images it has taken. NASA has decided to investigate an ancient river delta near the Martian equator.
A large number of deposits have been found in the vicinity of this delta that are very interesting. They include clay minerals and salts, basically everything that would lead you to conclude that if life did form, then this is the environment it happened in.
Around 4 billion years ago, there are oceans, rivers, and lakes on Mars. One day, an asteroid slams into the planet, leaving behind a crater 45 kilometers in diameter, the Jezero crater. 2 rivers fill the crater with water. A lake almost the size of Lake Constance forms. The lake doesn't dry out for millions of years. The river deltas along the former shoreline are still clearly visible today. NASA is studying the crater rocks using the sophisticated measuring instruments aboard the Mars Reconnaissance Orbiter. The crater rim consists of various types of carbonate rock. On Earth, carbonates like this are found at the bottom of lakes and oceans, where the remains of microscopic animals are deposited. This is the ideal place to search for traces of life on Mars. But what could these traces look like? Perhaps the same as on Earth. Here, complex biomolecules formed from simple chemical compounds in the oceans 3.8 billion years ago. The first single-celled organisms evolved. Microbes aggregated to form so-called microbial mats at the bottom of lakes and oceans, which fossilized over time. A new microbial film formed on the rock. Over millennia, so-called stromatolites formed. They are some of the oldest fossils on Earth. Something similar may be present on Mars too.
Assuming we do find traces of past life, it will be in the form of microfossils. That means sedimentary rocks, certain deposits, like stromatolites that were formed by cyanobacteria on Earth. This is a kind of rock today, but it was clearly formed due to the presence of these bacteria. And we hope to find similar sediments on Mars that would indicate the presence of life back then.
Perseverance receives help in its search from the air. It has a helicopter drone on board, called Ingenuity. Never before has a drone flown on an alien planet. Taking off with a helicopter on Mars is far from simple. The air here is as thin as it is at an altitude of 32 kilometers on Earth.
It will operate in a small radius of a few meters around the rover and observe things from above, something we haven't been able to do before. It will also help us decide whether it would be worth sending more instruments that can fly in future, something that's crucial for reaching places that would otherwise be inaccessible, like caves, and to look for life or maybe water and such things there.
Aside from cameras, Ingenuity has no instruments on board. The drone itself is the experiment. It's investigating how well flying in the Martian atmosphere works, and it expands the rover's range of movement.
Driving a rover like this isn't that easy. The camera might be 1.5 meters above the surface, but it only takes a small ridge, and you can't tell what's on the other side. You have to drive there to check it out, and if you can't continue, you have to drive somewhere else. It's a very tedious process. Now we can launch this small drone, and it can fly over and look behind the ridge, and we can say there's no point heading that way, we're better off turning left, and thereby extend the range and find the way to the interesting areas more easily.
It would be absolutely sensational if Perseverance were to transmit from Mars to Earth pictures of the kinds of fossils we find here in Australia. Unfortunately, it's unlikely that such fossilized microbes have survived on the surface of Mars for hundreds of millions of years. They've probably long since turned to dust due to the radiation. It's possible that all visible traces of life have been destroyed. Still, the rover may be able to find them nonetheless. With its X-ray spectrometer pixel, it can detect the tiniest of chemical changes in the Mars rock and look for so-called biosignatures, chemical compounds that are only created by biological processes. It would be the first direct evidence of extraterrestrial life.
Life on Mars. How likely is it really? Well, 3.5 billion years ago, the conditions for it were ideal. We know that for a long period of time, the temperature on Mars was above 0 degrees Celsius. And we also know that back then, it had a vast ocean. And we have a meteorite that we know came from Mars. Many years ago, NASA analyzed this meteorite and believed they'd found microorganisms inside. So they held a huge press conference about it. It later turned out, however, that they weren't microorganisms after all, just pure geology. So to this day, we still have no evidence of life on Mars. But even if we could prove the existence of primitive life on Mars, it still doesn't mean that there might be other forms of intelligent life elsewhere in our galaxy. It would just make it more probable.
Perseverance could deliver the answer to this question, quite literally to our doorstep, as it were, in the form of samples of Mars rock. The rover takes samples using a drill on its arm and packs them into special tubes. Then it deposits the samples at specific locations on the Martian surface.
And then a European rover arrives, finds these little samples, collects them all, packs them into a large container, and brings them to a small launch pad where a small American rocket is waiting. They're packed into this rocket and shot into orbit around Mars. There, the rocket releases this container to orbit freely around Mars on its own. And then another European mission will come and find this container, capture it, and bring it back to Earth.
Thanks to this collaboration between the European Space Agency ESA and NASA, we'll then have Mars rock on Earth, perhaps with evidence of ancient life. It will take until at least 2031, though, if everything goes according to plan.
If we were to discover that there used to be life on Mars, not only would we know that we're not alone, but we could say with certainty that life can form in places other than on Earth. It would give us reason to continue searching, and it would be pretty sensational.
It would mean that we're no longer unique, that life can emerge not just on the Earth, but can do so anywhere with suitable conditions that allow these processes to happen. The next question is, what does this life look like? Does it look similar to early life on Earth, that is, blue-green algae, single-celled organisms, and so forth? Or is it completely different?
But if there was life on Mars in the past, is it possible that it survived until this day? On Earth, we only find life where there's water. The surface of Mars is bone dry. The low atmospheric pressure means that water would evaporate within seconds. But there could still be water beneath the surface. Scientists have discovered evidence of several lakes deep below Mars' southern polar cap. The radar aboard the ESA probe Mars Express penetrates the 1.5-kilometer thick ice. The measurements show that under it lies water. It must be extremely salty because it's liquid, despite an estimated temperature of minus 68 degrees Celsius. The high salt concentration lowers the freezing point of the water. Scientists cannot rule out the possibility that life may still exist in such subterranean Martian reservoirs today.
Many scientists actually believe that life still exists on Mars today. It cannot be on the surface, though, as the Martian surface is extremely hostile to life. So we have to drill underground. It's quite possible that there are hydrothermal vents on Mars, and that there really are life forms there still.
These are geothermal springs in Yellowstone National Park in the United States. The water here is almost boiling and is as acidic as lemon juice. Despite this, the springs are home to life, to so-called extremophiles.
The extremophiles have shown us that on Earth, too, there's life in regions we previously considered impossible, like in the ice at the poles, in black smokers, on the ocean floor, in nuclear power stations subjected to radioactivity, in salt lakes. So that means that the range of conditions in which life can exist is far greater than we previously thought.
The European Space Agency ESA is also looking for life on Mars. In 2016, the Schiaparelli lander crashed, but the mothership, the ExoMars Trace Gas Orbiter, continues to circle the planet and study the Martian atmosphere. And a European rover will soon be rolling over the Martian surface in addition to Perseverance. Rosalind Franklin can drill up to 2 meters down into the surface and will look for traces of life there.
On a positive note, we're now coordinating the program profiles of these missions with one another. So ExoMars is doing different things than the American rover. We're specifically looking 2 meters under the surface to see if there's something like life there. The American rover isn't doing that.
The NASA and ESA Mars missions are ambitious. Perhaps they will soon answer one of the most intriguing questions for mankind. Is there extraterrestrial life? And they're laying the groundwork for the next big step, a manned mission to Mars.
Vana von Braun, the father of the moon missions in the 1960s and 70s, had a big dream. He wanted to go to Mars. For him, the moon was just a stepping stone. In the case of the moon, you need 2 or 3 days to get there and 2 or 3 days to get back. But Mars is in a completely different league. In order to understand this, let me briefly explain the situation. At the center of our solar system is the Sun. Here it is. The Earth orbits the Sun a bit further in. Here's the Earth's orbit, and a bit further out, we have Mars's orbit. If I want to fly from the Earth to Mars, I need to follow a so-called Raman transfer orbit. This is the energetically most favorable trajectory. And there's something else to consider. If I want to meet up with Mars here, when I set off from Earth, Mars must be roughly here. Because at the same time as I'm flying across here, Mars is moving toward this point as well. So I meet up with Mars here. But here's the thing, I obviously want to return to the Earth again. And to fly back, I need to follow another Raman transfer orbit. But when I set off, the Earth can't be just anywhere. It has to be roughly here. This means I need 200 days to get there. No more, no less. It's pretty much exactly 200 days. 200 days to get back again. And have to spend a little more than a year on Mars. So altogether I need 2.5 years for a complete Mars mission. And I can only do this every 2 years, because the Earth and Mars are only in this constellation every 2 years. We have the rockets necessary for such a mission, both NASA and Elon Musk. But that's not the problem. The real problem is guaranteeing the technical reliability of the mission for the entire 2.5-year duration. And in order to do this, we need the moon. We can use it as a proving ground to show that we can do it.
But before we set off to Mars, we're returning to the moon. Following the Apollo program of the 1960s and 70s, NASA has launched a new, ambitious lunar program, the Artemis program, named after the twin sister of the Greek god Apollo. In 2024, over 50 years after the last flight to the moon, Apollo 17, a human will once again set foot on the lunar surface. And this time, we're coming to stay. From 2028, there will be a permanent research station there.
Fortunately, the attention of many countries, states, and space activities is once again on the moon. It wasn't always this way. It had been forgotten. For a while, the moon was considered to be just a dead rock. But we now know there's water on the moon. We know that there's helium-3 in the moon. The moon is much more exciting than we think, which is why there's now a worldwide movement to fly to the moon as well.
The moon has become scientifically interesting again, and it's of strategic importance. The destination of the Artemis missions is the southern polar region, because there's water ice there. The moon is not as arid as it was long presumed. SOFIA, the flying telescope of NASA and the German Aerospace Center, detected finely dispersed water molecules in the moon dust. Not much, only about 1/3 of a liter per cubic meter of lunar regolith. Perhaps it was brought to the moon via small meteorite impacts encapsulated in tiny glass pearls. Water is the key raw material on the moon, too. Astronauts need it to survive. And water can be split into hydrogen and oxygen, which make rocket fuel. Construction of a new space station that will orbit the moon is scheduled to start as early as 2023. The Lunar Orbital Platform Gateway will be the counterpart of the International Space Station. Like the ISS, it will consist of separate modules and is a collaboration of various countries and private aerospace companies. In the future, astronauts will travel to the moon via the Lunar Gateway.
The Lunar Gateway is a kind of bus stop orbiting close to the moon from where it's easy to descend to the lunar surface, and that can be used as a staging post. It's a big program, and NASA naturally imagines it as being the stepping stone to Mars.
The moon will be our proving ground, our research laboratory, perhaps even our gas station and springboard to Mars. NASA presents the new spacesuit. A woman is to set foot on the moon for the first time as part of the Artemis program. The new suits offer substantially more freedom of movement than previous models. They work at temperatures ranging from minus 150 to plus 120 degrees Celsius. They're intended to be used on later Mars missions too. Life support systems for the astronauts, habitats to protect them against the deadly radiation and cold, the mining of water and oxygen, and the production of rocket fuel. All this is to be tested and perfected on the moon.
I would say our moon is a bit like an extra continent. It's really close, practically on our doorstep. We saw that with Apollo. You can fly there in 3 days and back in another 3. And 100 years ago, you couldn't even get from England to America in 3 days. So I'm pretty sure that the moon will remain a target.
It would make flying to Mars much easier if you could use it as a stopover, as it were. You'd just have to first head to the moon, and then you can board the spacecraft that will ultimately take you to Mars. You wouldn't have to escape the Earth's atmosphere with this vehicle, and thus you could have a break during the long flight in a sense.
Mankind is getting ready to take the next big step. And as in the 1960s, the journey begins with fire and smoke.
The key to a successful flight to the moon, and indeed Mars, is a highly efficient and reliable rocket. Because for every ton we have to transport to the moon, we need 100 tons of fuel. Every % of efficiency really matters here. So, what rockets do we have? Well, in the middle here, we see the old Saturn V from the 1960s. These are the 2 new rockets that are currently under development. On one side, Starship from SpaceX, so Elon Musk. And on the other side, the SLS, which stands for Space Launch System, from NASA. Incidentally, the rockets are about 120 meters tall, which is roughly the height of the Cologne Cathedral. And each rocket weighs about 3,000 tons. It's interesting to note that although the objectives of the new rockets are the same, their development processes were completely different.
The Space Launch System, the biggest, most powerful, and most expensive launch vehicle in the history of NASA. Depending on development stage, it will be able to deliver a payload of up to 130 tons into low Earth orbit or 45 tons to the moon. The SLS is being built by Boeing using proven technology. The solid rocket boosters and upper stage engines stem from the Space Shuttle program, which was developed in the 1970s.
It's definitely state-of-the-art, technology-wise. The Space Shuttle main engine is basically the most efficient engine ever invented and built in the history of mankind. The only problem is that it's very expensive.
Because there aren't enough shuttle engines left for the Artemis program, NASA has ordered 24 new ones at a cost of nearly $150 million apiece. The SLS is not reusable, so 4 of these engines are lost with each launch. The cost of an SLS rocket launch is estimated at around $2 billion, and developing the SLS devoured $20 billion even before the first launch.
It's a question of risk. If I, as an institutional service provider, want to do something, I want to minimize the risk involved. I'm using public funds, and I want everything to function 100%. If I were approaching things as a private entity, I would allow more risk. As a result, I have a chance of achieving the same goal with lower costs.
Making space travel radically less expensive is the goal of SpaceX founder Elon Musk, and also Stefan Brischenk, COO and chief developer of Rocket Factory Augsburg. The Bavarian rockets aren't intended to fly to Mars, but rather to cost-effectively put small satellites into low Earth orbit. The principle, industrial rocket production instead of rocket science.
We're trying to approach things from an industrial perspective. We come from an industrial background. You can picture it like this. We're more like a car workshop that has the goal of building a cost-effective rocket. We're not starting in a lab or clean room and trying to push the boundaries and achieve the maximum that's technically feasible.
That's why it looks like it does here. High-tech meets craftsmanship. Rocket Factory fabricates complicated components itself. Others, like the large stainless steel tank, come from subcontractors, and partly from the automotive industry. The engines are 3D printed.
It speeds up the development process, as we can modify things and try them out quickly. For instance, if we notice that the heat buildup at a particular point is too great, we can change the design of the cooling circuit to increase cooling there. That is, I can program it, print it out, finish it, and test it immediately. It's essential that we can precisely replicate parts later on. I only need to configure this machine once to get the same result every time. This will become important when we increase production from 1 rocket to 20. It allows us to scale things up easily. We just have to buy more 3D printers, set them up properly once, and then we can print engines like on an assembly line.
Mass production is the basic concept of SpaceX and Elon Musk, too. The new giant rocket ship, Starship, is intended to take payloads of up to 150 tons or 100 astronauts into space. It is intended to replace all other SpaceX rockets, put satellites into orbit, and fly to the International Space Station, the Moon, and ultimately to Mars. The Starship consists of 2 stages. The first stage, named Super Heavy, is designed to take the rocket fitted with 31 Raptor engines into Earth orbit. Here, the upper stage separates from the first stage, refuels if necessary, and sets off on its mission. In August 2020, the first Starship prototype flew to a height of 150 meters before landing again. Following the principle of trial and error, SpaceX rapidly develops its technology further. Risks and setbacks are factored in, and they're real. In December 2020, the 8th prototype climbs to an altitude of over 12 kilometers. The rocket quickly gains height, then starts its descent, flips horizontally to slow down as planned, and then vertically again, ready for touchdown. The landing itself, however, doesn't go quite as planned. Barely 2 months later, the next flight with rocket number 9 meets a similar end. "We've just got to work on that landing a bit," was the laconic comment from SpaceX.
At SpaceX, they call it sparse matrix engineering. It means that engineers make decisions without filling in all the blanks before proceeding. I wouldn't consider it shooting from the hip, but you make decisions faster in order to move forward more aggressively. And there are naturally risks involved. The engineers working there are allowed to take greater risks and achieve their goal faster as a result.
SpaceX estimates that a Starship launch will cost $2 million. That would be 1,000th that of an SLS launch. The reason? Industrial mass production. Elon Musk wants to build up to 1,000 Starships in 10 years, and the Starship is completely reusable. And that's not the only thing that speaks in favor of the Starship concept compared to the SLS. Its Raptor engines run on oxygen and methane. Both can be mined on Mars for the astronauts' return journey to Earth. But for humans to survive on Mars, it will take a lot more than that.
So, what are the living conditions like for humans on Mars? Let's take a look at the atmosphere first. The air pressure is just 100th of that on Earth. This means you have to wear a pressure suit at all times. And if you always walk around with one of these on, temperatures of -60 to +20 degrees Celsius at the equator are no problem. But what's the deal with the infamous Martian storms? Well, with such a thin atmosphere, they're more of a gentle breeze. One issue is the CO2 atmosphere. There's no oxygen up there, so you'd have to wear oxygen cylinders on your back all the time. There are basically only two real problems. One is the cosmic radiation that bombards the surface unimpeded. Let's put it like this. A person on Earth has a 20% risk of getting cancer. Spending 2.5 years on Mars will increase this by another 20%. So 40% in total, which is quite high. But the really big problem is that the vast amount of fuel needed for the return journey to Earth would have to be manufactured entirely on Mars.
Future astronauts on Mars will need protection from the vacuum, cold, and radiation. They'll need air to breathe, more specifically, oxygen. This is present on Mars, in abundance, in fact.
Oxygen, there's a lot on Mars. Mars is also known as the red planet, and it's red because it's rusty. This is iron oxide, which means there's a great deal of oxygen in the Martian crust and rocks. There's also a lot of oxygen in the atmosphere too, albeit not as pure oxygen, but bound as carbon dioxide. Whether we split the carbon dioxide or extract the oxygen from the rocks because we want to mine iron anyway, the element oxygen is definitely present. The only question is, how easily can we extract it? And how efficient and reliable is the process?
The Perseverance rover is tasked with testing it, and that's why MOXIE is on board. The device will use electricity to split CO2 in the Martian atmosphere into oxygen and carbon monoxide. MOXIE is about the size of a car battery. Future systems would have to be 100 times bigger in order to generate enough oxygen for the astronauts to breathe. The Mars travelers will also need oxygen for their return flight as part of the rocket fuel. The other part, hydrogen or methane. Both could likewise be manufactured on Mars.
When we eventually fly to Mars, it's likely that 3 or 4 spacecraft will have been sent in advance with material, equipment and fuel, and also a small plant to synthesize fuel to get them home again. It's a very different proposition to a moon mission, where you fly there, stay for a few hours and then fly back again. Things won't be quite that straightforward with Mars.
The astronauts will have to live on Mars for over a year before the next window for a return flight. Perhaps in modules like this. It was developed by Christiane Heinecke of the Center for Applied Space Technology and Microgravity, ZARM, at the University of Bremen. A module from the Moon and Mars Base Analog Project, or MAMBA for short, stands in a laboratory hall at the center. ZARM scientists have already spent 2 test weeks working in here, albeit without the life support systems that would be necessary on Mars.
If I were to simply go outside on Mars, I'd either suffocate or experience a very unpleasant death anyway. This habitat must ensure that I can breathe. It has to withstand the pressure difference and protect me from the cosmic radiation. Though Mars has a thin atmosphere that filters out a small amount, a great deal still comes through.
6 modules like this will later be joined together on the Moon and Mars to create a self-contained system, a so-called habitat, a living space for the astronauts. The individual modules serve different functions and are equipped differently, as a laboratory, a workshop, or for sleeping.
Our plan is to construct a large artificial cave around the habitat with moon rock or Mars rock. Whether it will be made by 3D printing, using individually sintered blocks, or simply by piling up rocks is irrelevant. In the end, there'll be a thick layer of rock surrounding the habitat to protect it from the cosmic radiation.
There are basically 2 concepts for such habitats. Rigid metal constructions like the MAMBA modules, or inflatable modules made from some sort of fabric or foil. With this concept, developed by ESA, the modules are buried in moon craters to protect them from the radiation.
The big advantage is that the transport volume is relatively small while offering a large amount of space when erected on site. The disadvantage is that you then have to assemble everything on site. You have to bring in all the tools and equipment, through the moon dust, airlocks, in and out. What you save on transport, you trade for all manner of problems down the road. Which is why we said for the first base on the moon or later on Mars, it will be much easier if we have the habitat more or less completely assembled as a single module. The finished module will naturally be much heavier and larger than an inflatable one, but once it's on the moon, it's finished.
Scientist Cyprien Verseux is conducting research at SARM on cyanobacteria. Also known as blue-green algae, they could play a key role when it comes to living on Mars. They grow by photosynthesis, can generate oxygen and extract nutrients from rock. With their help, oxygen, fuel, and even food could be produced on Mars. To do this, the cyanobacteria basically require gases found in the Martian atmosphere and water.
You could feed them almost directly with what you find on Mars. And once you've grown them, you can use them for making oxygen, for making dietary protein, but you could also use them for making nutrients for other organisms, like plants or other microbes. And like this, make a small-scale ecosystem, which is based almost directly on what you find on Mars, and that can produce most of what astronauts need to survive.
How well do cyanobacteria grow under Mars-like conditions? This is what Verseux is investigating with his experimental setup he designed himself. The bacteria are grown in these flasks. The pressure, composition of the air, and temperature are different in each one, and they differ only slightly from the conditions on Mars.
You want to be as close as possible to the Martian atmosphere so that the system would be easier for engineers to design. Because if you have a big pressure difference between inside and outside, you need something very sturdy and so very heavy. So we're trying to find out how close you can get to Martian conditions while still having bacteria that can grow efficiently.
Future Mars explorers won't have to subsist on algae alone, of course. They will likely bring a large portion of their food from Earth in the form of freeze-dried rations, like the astronauts on the ISS.
I think it will be a combination of different approaches. You'll have freeze-dried food, but you'll still end up having to cultivate fresh plants, not least because you're in this rocky desert. You want to see a plant now and again.
Growing vegetables in a greenhouse works, even if the conditions outside are not exactly hospitable. This has been demonstrated by the Eden ISS greenhouse in the Antarctic. A year-long test of vegetable cultivation for Moon and Mars missions was conducted here on behalf of the German Aerospace Center. The harvest, 300 kilograms of salad plants and vegetables, as well as herbs and even strawberries. And all this from just 13 square meters of cultivated space, without soil or sunlight. Instead, electronically controlled and optimized. Although the team at the German Antarctic station Neumeier 3 was cut off from the outside world, the scientists were served fresh vegetables on a regular basis.
That's right. We could grow vegetables in greenhouses on Mars. Incidentally, the movie The Martian depicted this in an authentic and above all very vivid manner. So that's how humans could colonize Mars. You could ask yourself, why should we bother? And the answer is, because then we actually could. And the next question is, when will all this happen? Well, it certainly won't be before the end of the 2040s. Probably more like the 50s or maybe even the 60s before we're ready.
SpaceX founder and chief engineer Elon Musk wants to save mankind. If the Earth should one day become uninhabitable due to an asteroid impact, the eruption of a supervolcano, or for some other reason, we'll need a foothold on another planet.
The main reason I'm personally accumulating assets is in order to fund this. So I really don't have any other motivation for personally accumulating assets except to be able to make the biggest contribution I can to making life multiplanetary.
Namely, on Mars. If it were up to Elon Musk, there would be self-sufficient cities on the red planet by 2050. He estimates that it will require 1,000 starships to bring the material and crew to mankind's new home. It will take 20 years to transport and build the infrastructure, from the fuel plant to the pizzeria.
The goal is get enough tonnage to Mars and enough people to make Mars self-sustaining as quickly as possible. 100,000 tons, maybe 1 million tons. So you can't be faffing around with these expendable rockets. They're a joke. They're absurd. Even Saturn V is tiny potatoes.
Another reason why SpaceX's Starship is not only huge, but designed to be completely reusable too. Thanks to industrial mass production, the rockets are designed to bring down the cost of a flight to Mars from around $10 billion per seat to $140,000. But is this actually realistic?
The vision of traveling to Mars has always fascinated people. It takes people who can drive things forward and have or can mobilize the necessary resources. Otherwise, you can't turn a vision like this into reality. It will happen sooner or later.
Elon Musk is doubtless a visionary, and he's accomplished a lot, an incredible amount, which is why I admire him. He's a great businessman, too. He's negotiated great business models with NASA. He's consistently taken a visionary approach and done things we simply couldn't have.
Ich halte Elon Musk für einen sehr großen Showman.
I consider Elon Musk to be a great showman who made his money in completely different areas and was probably fascinated by space travel as a child and said, I want to do that when I grow up too. But if you look at his projects, you have to ask what have they actually accomplished thus far. He's got as far as the International Space Station, 300 kilometers above the Earth. But when you consider all the things he's talked about, when we'll be on Mars and so on, well, I'll see how things go over the next few years.
Ich gucke mir das an die nächsten Jahre.
Even if humans do actually settle on Mars in 50 or 100 years' time, Mars is no second Earth. But perhaps it doesn't have to remain an inhospitable desert. Terraforming could, in theory, turn the clock back 3.5 billion years and transform the red planet into a blue planet once again.
First, you need to start heating it. There are different ways of doing it. I mean, some people are suggesting having some mirrors in orbit to, focus sunlight. There is an extreme solution that Elon Musk famously talked about, which would be to drop some nuclear bombs on the poles. There are many, many ways it could be done, or it could be also starting, bringing some greenhouse gases. And then once you start heating it a bit, then the carbon dioxide ice would sublimate. So it basically you would have carbon ice that would become carbon dioxide as we know here. And then with the greenhouse gas, it would heat more, which means that more carbon dioxide would come out and so on. And then once it's warmer, you could start thinking of bringing, cyanobacteria, for instance, that would do photosynthesis, create oxygen and so on. So that would be a very slow process and you would have several steps, but there are several ways in which it could be done.
In time, you could eventually cultivate an increasing number of ever more discerning plants, until at some point the atmosphere is dense enough for future Mars inhabitants to venture outside without pressure suits. It would take 500 to 1,000 years. It would take even longer before sufficient oxygen has accumulated in the atmosphere for it to be breathable, probably around 1 million years. Unfortunately, the hard-won Martian atmosphere wouldn't be permanent, as Mars lacks a protective magnetic field. The radiation would blow it away again after a few 100 million years, the way it did 3.5 billion years ago.
Terraforming Mars means making it blue and green. In theory, say the scientists, it ought to work just fine. Whether it actually works in practice remains to be seen. So what does the future of manned spaceflight look like? It's easy to answer. First, we'll fly to the moon, have a manned moon base, then to Mars in the 40s or 50s, including a permanent base. Will we then venture even deeper into the solar system? Not a chance. Why? Well, the temperatures present somewhat of an obstacle. If we fly toward the Sun, to Venus or Mercury, the temperatures are in excess of 400 degrees Celsius. If we fly away from the Sun to the gas giants like Jupiter and beyond, the temperatures fall below minus 200 degrees Celsius. These are not conditions for human beings. Even the moons are too cold. The only things out there that could be of interest to us are the oceans beneath two of the moons. But we can visit them with unmanned missions. Whatever happens, our moon will always be there for us to use as a proving ground. And I have to say, I'm very grateful we have it.
Mankind is about to take a giant leap, like Neil Armstrong in 1969. Astronauts are set to return to the moon and operate a research station there. Experts are divided as to whether or not humans really will fly to Mars in the near future.
From a technical and engineering perspective, it would be feasible to fly to Mars within the next 15 to 20 years. What's always been lacking, however, is the political will to actually do it, and therefore the funding to really see it through now.
I don't think we'll see astronauts heading to Mars in the near future. Mars isn't like the moon that constantly circles around us. Mars has its own orbit around the sun. This is why we only meet up with it every 2 years. And it's also why a trip to Mars and back takes 2 years. And when you consider the radiation, technology, and all the other issues, it's simply too difficult and complicated to be attempted at the moment.
The big question is whether we will have the investment and the focus needed to do it. I'm quite hopeful that it will happen, otherwise I would not be working on that. I would be losing my time.
Eine Reise zum Mars ist eine so
A trip to Mars is such a huge undertaking that the entire world would have to cooperate. It won't be one American, it won't be a Musk. It won't just be NASA, rather the American, Chinese, Russian and European space agencies will have to work together. In that sense, it's good news, because if everyone is working together, it means we've solved all the other problems in the world for the time being.
If enough money can be made from space travel by mining raw materials on asteroids, for instance, the question of funding won't come up anymore. The boundaries will then be pushed even further.
We could go to Ceres or any of the asteroids, the moons of Jupiter, although there'd be quite high radiation around there, and then out to Saturn, eventually getting out to the sort of Kuiper belt, Earth cloud, and that kind of thing, the outer solar system. So Starship, once you have propellant depots, you can kind of like planet hop or moon hop around the solar system.
This is no doubt a very far-off vision, but in the end, every great journey begins with one small step.
To sum it up, we will return to the moon before this decade is out. There, we'll test the technologies that will be needed to send a manned mission to Mars. This will likely happen in the 2030s. But it probably won't be until the 40s that we'll have a permanent research station there, because that won't exactly be cheap. Whether in the 2040s or even the 50s is pretty much secondary in light of the fact that these first Mars flights will no doubt go down in history as one of the greatest achievements of humankind.